Dear participant, we continue the work of our annual international conference on algebraic and geometric method of analysis. The first presentation today related to the algebraic methods. In recent year, many outstanding mathematicians have joined our conference, and I am pleased to enunciate the first speaker, Professor Dean of Mechanic and Mathematical faculty at Taras Shevchenko Kiev University, Oksana Bezushchak, with a presentation on Clifford algebras on infinite-dimensional vector spaces. Please.
Я, звісно, що можу говорити українською, але була анонсована англійською мовою. Я рада всіх бачити колег, dear participants of the conference, esteemed colleagues and friends from around the world. It's my great pleasure and a big honor to speak on the conference Algebraic and Geometric Methods of Analysis. Our presence here today due to this terrible time for Ukraine due to the war is a testament of our resilience and for our colleague abroad, a profound act of solidarity and, of course, of support of Ukraine, of our struggle. And thank you very much for organizers for inviting me, and thank you, all of us, for our presence here and contributions. I wish all of us productive discussion, inspiring discoveries, and victory to Ukraine. Today we talk about Clifford algebras of infinite-dimensional vector spaces. Clifford algebra was first defined by William Clifford, roughly 1 year before his death. He passed away at a very young age, and in 1878, Clifford greatly expanded his work onto Grassmann's work to the form what we now usually called the name for such form as a Clifford algebra in his honor. A thought Clifford himself chose to call them as a geometric algebra. This is, as for me, this is geometrical object. But let us start from the very beginning, from the definition. Let us consider vector space, the field of characteristic not equal to 2, and we consider a mapping from the vector space to the field as a quadratic form, as a mapping which satisfied the following condition on the slide, and the quadratic form is non-degenerate if the corresponding linear form is non-degenerate. Then the Clifford algebra is the algebra which is generated by the vector space V multiplicative identity and defining relations on this slide. We suppose that round field is algebraically closed and quadratic form is non-degenerate, and when the dimension of the vector space finite, then the dimension of Clifford algebra is equal to the 2 to the power, which is equal to the dimension of the vector space. And due to the book of Nathan Jacobson, Structure and Representatives of Journal Algebras, when the dimension of the vector space even, then the Clifford algebra is isomorphic to the matrix algebra of matrices of order which equal to the half of the dimension of the vector space. And in the case then the dimension of the vector space is odd, then the Clifford algebra is isomorphic to the direct sum of the matrix algebras of matrices of corresponding order which is equal to the 2 to the half of the n minus 1, where the n is the dimension of the vector space. Let us consider some bases of vector space V. Such bases we can indices by the ordered set of indices. Then, due to the Grobner-Shirshov algorithm, we can consider a set of ordered finite product of the vector from this basis. This ordered product is the vector which is indices of the indices from some increasing set, finite increasing set of the indices from our ordered set of indices, and then such ordered product form a basis of Clifford algebra. We consider only countable dimensional vector space, so that is why, as a set of integers, we can see integers of positive integers. We can consider a set of positive integers. Now, let me divide the Clifford algebra into two components. So we consider a gradient of the Clifford algebra by the cycle group of order 2. It means that Clifford algebra presents as a sum of even and odd component, where even component is the component which consists of the infinite sum of finite product, of finite even product of the vector from the vector space, and the corresponding odd component consists from the infinite sum over the odd finite product of the vector from the vector space. What can we do in infinite dimensional case? We consider infinite dimensional countable case. Some definitions, and let me mention some results. Due to Alexander Kurosh and Gyötr Kyote, we will call an associative algebra over a ground field as a local matrix algebra if for each finite subset of elements from this algebra there exists some subalgebra of our algebra containing this subset and which is isomorphic to matrix algebras. And such algebra is unital if it contains a unit. In our joint paper with Bogdano-Olinik in journal Algebra Application, we proved that when the vector space in infinite dimension over algebraically closed field, this is a very important satisfying condition. And when we have a quadratic form which is not degenerate, then the Clifford algebra is a unital locally matrix algebra. In 1931, Gyötr Kyote proved that in the case of every countable dimensional unital locally matrix algebra, such algebra is isomorphic to a tensor product of matrix algebras. But for unital locally matrix algebras of uncountable dimensional, this is no longer true. There are some examples, there are very technical examples due to Alexander Kurosh. We did some series of examples in our joint paper with Bogdano-Olinik in our paper in Bulletin Mathematical Science. And now let us start with explicit decomposition of countable dimensional Clifford algebra into a tensor product of matrix algebras. The tensor product in our mean, this is product which is all elements from such infinite tensor product, but finitely many, are identity. This is some remark. So we consider orthonormal basis of the vector space. And let us fix some increasing sequence of even numbers because we need to admit Clifford algebra as the tensor product of matrix algebras, not direct sum. So, and let us consider the subspace V sub I of the other space V, which is spanned by the vector from the orthonormal basis, which is indices. The indices from our increasing sequence of even number between two adjacent elements, and then subalgebra of the Clifford algebra, which is generated by our subalgebra V sub I, is isomorphic to corresponding Clifford algebra in our common meaning. So, as well as for whole algebra, Clifford algebra, let us consider the grading by the cycle group of order 2 into even and odd component. It means that we consider the dividing of the Clifford algebra, which is generated by subspace V sub I, into two components, odd and even. Even components span by the finite product of the elements from orthonormal basis, which is indices, the indices from our increasing set of even positive integers between two adjacent elements, and corresponding odd component also spanned by the finite product corresponding vectors from the orthonormal basis. And also fix the product of the first elements from our orthonormal basis, and let us denote this product, finite product, by symbol C sub A. And now we consider the sequence of algebras. The first algebras A sub 1 is the Clifford algebra, namely generated by the vector space V sub 1. And another one is the sum of the component of the Clifford algebra, even and odd, but the odd component V times by the element C sub I. Why do we need the times the odd component by some elements? Because we need that the such subalgebras E sub I to be commute. So, theorem 2, due to the paper in contemporary mathematics, it will be appear in this year. So the Clifford, first of all such subalgebras E sub I is a Clifford algebra, which is generated corresponding vector space V sub I, and Clifford algebra admit a decomposition into infinite tensor product, countable tensor product of such subalgebras. Let me mention some more definition. Linear mapping of associative algebra over field F is a derivation if the product role on the slide hold. Also, the mapping commutation with a fixed element is an inner derivation, and the conjugation by some invertible element we call inner automorphisms. So one more definition: Bogoliub of automorphisms and Bogoliub of derivations. Let us consider some orthogonal linear transformations that preserves the quadratic form. It means that the quadratic form acts of the image of the orthogonal linear transformation into any vectors of the vector space. It means that we maps only by using the quadratic form. And it is easy to see that orthogonal linear transformation uniquely extends to the automorphism of the Clifford algebra in the natural way on the slide, and such automorphisms are called Bogoliub automorphisms. And Bogoliub derivations, we consider skew-symmetric linear transformations. It means that such linear transformations and non-degenerate quadratic form satisfy the following condition on the slide. And in this case, the skew-symmetric linear transformation uniquely extends to the derivation of Clifford algebra, also in the natural way on the slide, and these derivations are called Bogoliubov derivations. There are known families of derivations and automorphisms of Clifford algebras in infinite dimensional case when the quadratic form is non-degenerate. The inner derivations and inner automorphisms and Bogoliubov derivations and the Bogoliubov automorphisms and no other derivations and automorphism can be known. In 2022, in the site Math Overflow discussion, Professor Ludovic put the question, is an arbitrary automorphism of Clifford algebra continuous? Some remark about what do we mean by the continuous of the automorphism. Continuous in the sense of the norm algebra. It means that when we assuming that the ground field is a field of we will assume as a field of real number, then we consider quadratic form as before as positive definite. We will define a structure of norm algebra on Clifford algebra, solve the continuous in this sense. Solve the question, is arbitrary automorphism of Clifford algebra continuous? And some remark that inner automorphism and Bogoliubov automorphism are continuous. In our talk, we first describe all derivations of the Clifford algebra, not only inner and Bogoliubov derivations. And the second, we construct an algebraic automorphism of Clifford algebra over a field of real number that is not continuous, and we will give a negative answers to the question of Professor Ludovic. So we consider Clifford algebra countable dimensional over algebraically closed field of characteristic not equal to 2. We need definition. We have to divide the derivation into two classes, even and odd. We will call it derivation of, and every derivation of Clifford algebra will be even or odd. We call a derivation of Clifford algebra even if this derivation maps the even component into even and odd into odd. And we call it derivation of Clifford algebra odd if it maps the odd component into even and even into odd. And some remark, Bogoliubov derivations are even because they don't change the parity of the length of the presentation of the elements through the basis of Clifford algebra. And inner derivation can be even or odd. Next theorem. In the journal Contemporary Mathematics will be appearing this year, I hope. Also, we consider countable dimensional vector space. The field is algebraically closed, characteristic not equal to 2. And let me fix some arbitrary orthonormal basis of our space. Then the first, any non-zero even derivation of Clifford algebra can be uniquely represented as an infinite sum, where the infinite sum of adjoint derivation by the elements V sub s, where the element V sub s, this is element which denote the finite product of elements from our orthonormal basis, which is indices, the finite indices from increasing finite indices from the set S, and the sum is taken over by the finite non-empty subset of the set of positive integers of even order, such that an arbitrary positive integer lies in no more than finitely many such subset. And second, non-zero odd derivation of the Clifford algebra can be uniquely represented as an infinite sum. Also, this infinite sum of the joint derivation times some elements from the algebraically closed field, and the sum is taken over the finite subset of odd order of the set of positive integers, such that the arbitrary positive integer lies in all but finitely many subsets from the set of positive integers. And some remark derivation will be inner if and only if such sum is finite. Some very important remark. Of course, we need, before we formulate the theorem, we need to check that this infinite sum, what we are talking about in the last theorem, makes sense, and such infinite sums define linear operators. In the first case, for even derivation, if we consider some positive integers and if we consider the finite non-empty subset of set of positive integers of even order, then our joint derivation x of elements v sub I trivial, it means that v sub s and v sub I commutes. Hence, for arbitrary element from Clifford algebra and non-zero even derivation, our sum is infinite, but when we add this sum into elements from the Clifford algebra, we obtain the finite sum. In the second case, we have something similar. If S is finite subset of odd order, and in this case, we consider a positive integer that belongs to our set. Then also v sub s and v sub I commute, and we have infinite sum as which present our derivation, our odd derivation. But when this sum of the elements of Clifford algebra, we will have a finite sum. Therefore, our infinite sum makes sense, and therefore define linear operators. Speaking a little about the proof of the theorem, the proof is completely based on the paper from the Journal of Algebra. In this paper, we describe derivations and automorphisms of all countable tensor product of matrix algebras. And by the result of theorem 2 before, in our joint paper with Bogdan Alinik, we proved that countable dimensional Clifford algebra is isomorphic to countable tensor product of matrix algebras. Therefore, we consider an associative algebra as a countable tensor product of matrix algebras, and we need some more definition. We will call a system of non-empty finite subsets of the set of positive integers as a sparse system if the first for any set from this sparse system, all non-empty subset of such set also lie in sparse system. That is why the name is spar or sparsity. And an arbitrary element from the set of positive integers lies in no more than finitely many subsets from the sparse system. Some notation, and let us denote by symbol A sub s, big S, where S is the set of which consists of the finite set of the indices from the set of positive integers, and let us denote by symbol A sub s the finite tensor product corresponding matrix algebras. And for each subset from the sparse system, let us choose some elements from finite tensor product. Then we consider the sum of a joint derivation by the elements A sub s, where the sum is taken over for all set from the sparse system, and then such sum convergence in the Tikhonov topology to a derivation of our infinite tensor product, countable tensor product. Indeed, when we choose arbitrary element from tensor product, then, because the support is finite, this element belongs to some finite tensor product of matrix algebras, and because of sparsity of our system, for all but finitely many subsets from the sparse system, we have that joint derivation x of our element from the infinite tensor product trivially. In a paper from Journal of Algebra, we proved that the Lie algebra of all derivations of countable tensor product of matrix algebras is the union of this set. The set consists of the sum of a joint derivation. The sum is taken over for the all set from the sparse system, and the union is taken over all sparse system of the subset from the set of positive integers, and this union present the Lie algebra of all derivations of countable tensor product. And for proving our main result, we just applied the last theorem to the decomposition of Clifford algebra, what we are talking about before, into a tensor product. And then consider the convergers in the Tikhonov topology our set of the derivation. We get the infinite sum from the theorem 3. In the first case and second case in the odd and even derivations. In some remark more, a little bit comment why do we need the sparse of system? Not only because we need to use our previous theorem, but also in our paper in Journal of Algebra, we also prove that the dimension of the Lie algebra of all derivation of Clifford algebra, we talk about Clifford algebra, is equal to the cardinality of the field F to the power, which is equal to the dimension of the vector space V. And in fact, for proving the theorem, we use sparse system for proving the theorem, because we have to define some basis of. We proved it's about the local matrix algebra. In the case of Clifford algebra, we need to define some basis of Clifford algebra due to Grotner-Shishov basis. So let us back to Bogolyubov derivations and how the Bogolyubov derivations fit in our description. Next theorem, also from the paper from Contemporary Mathematics, we consider countable dimensional vector space over algebraically closed field. We fix some arbitrary orthonormal basis. And even derivation of Clifford algebra is a Bogolyubov derivation if and only if the derivation presents as the following sum on the slide, and moreover, this presentation is unique. And also, like in the theorem 3, we need to think about does this sum make sense? Also, it makes sense because the set of the indices is finite. And corollary, the Bogolyubov derivation, which is corresponding to a skew-symmetric linear transformation, is inner if and only if our skew-symmetric linear transformation finitary, and it means that the dimension of the image of the our linear transformation is finite. And some remark about Bogoliubov automorphisms. In 1972, Pierre de la Harpe proved that a Bogoliubov automorphism, which is corresponding to a orthogonal linear transformation, is inner if and only if our orthogonal linear transformation finitary. It means that the identity except our orthogonal linear transformation has finite dimensional image. And now let us construct an algebraic automorphism of Clifford algebra that is not continuous. Continuous, it means we get a norm on the upper Clifford algebra. So for that, let us start with a trace construction that applies to all unital local matrix algebra, not only for Clifford algebras. For that, let us denote for unital local matrix algebras the set D of A, the set which consists of all positive integers such that there exists a subalgebra with unit which is isomorphic to matrix algebras of matrices of order which is equal to the corresponding positive integer. And lemma, suppose that characteristic of the field is coprime with all integers from the set D of A, and then there exists a unique linear functional, and moreover, for an arbitrary matrix subalgebra from our algebra A with unit and which is isomorphic to matrix algebra, the restriction of our functional to such subalgebra coincides with the normalized matrix trace. Now, as a field, we consider the field of real numbers, and we also consider a positive definite quadratic form. Our vector space is countable dimensional. And before we proved that Clifford algebra, our algebraically closed field is admit decomposition. But now we consider a field of real numbers. Therefore, since the quadratic form is positive definite, it follows that for any subspace from our space of even dimension, because due to that Jacobson from his book, or maybe somebody proved it before, for even dimension, the Clifford algebra is a matrix. For infinite dimension, the Clifford algebra will be matrix subalgebra. So we consider subspace of even dimension, and then the Clifford algebra, which generated this finite dimensional even subspace, is isomorphic to a matrix algebras, and consequently the Clifford algebra is a unital local matrix algebra over a field of real numbers. In our joint paper with Bogdanov, Linek in journal Algebra Application, we proved that the set D of A in the case of Clifford algebra consists of the whole power of the positive integer 2. And since the characteristic of the field is equal to 0, and the Clifford algebra over a field is a unital local matrix algebra by lemma, there will exist a unique trace functional, and then the Clifford algebra will be equipped with an involution that leaves all elements from vector space V invariant. It means that if the element presents as the sum, then we define a conjugation via the following formula on the slide, and to define the norm of elements by the trace, And this makes Clifford algebra a normal algebra. Then we can choose an orthonormal basis of vector space. And since vector space is countable dimensional, we can, so as before, we consider the set of indices as the set of positive integers, and also we will be use the notation as v sub s is a finite product of the elements from our orthonormal basis, which is indices the element from set S. And by the theorem 2, we identified Clifford algebra with tensor product of matrix algebras of matrices of order which is equal to some formula on the slide. And now we consider matrices X sub I and A sub I, where by symbol A sub k we denote the identity matrices of order k. And then we consider a conjugation automorphism V sub I by the element X sub I. X sub I is will be exist this conjugation automorphism will be exist, and then such conjugation act of the matrices A sub I as these matrices times its indices. The sequence of the finite product of such conjugations converges in Tikhonov topology to the automorphism of whole Clifford algebra. Because indeed for arbitrary element from Clifford algebra, the sequence of this automorphism V sub I, etc. stabilized. It means that the product of automorphism takes the same values starting from the indices n, but from one point of view, the sequence I sub I times its indices converges to 0, whereas the sequence of image of the automorphism of Clifford algebra into such sequence is equal to A sub A, this matrix is A sub A, which it does not. Hence, our automorphism is not continuous. But of course, some further directions. It would be interesting to construct such automorphisms of Clifford algebras where the dimension of the vector space is not countable, in particular for separable Hilbert space. But we have, of course, it's not obviously, we have some problems because as we showed in our joint paper with Bogdan Olinik in Bulletin in Mathematical Science, the Clifford algebra of Hilbert space is not isomorphic to infinite tensor product of matrix algebras. Thank you for your attention.
Thank you very much.
Thank you very much for such interesting and useful presentation.